The Canadian Sweeping Energetic Particle Telescope, known as SWEPT, is the radiation detector designed to provide accurate measurements of the high-energy proton and electron radiation experienced by the International Space Station. SWEPT will be the first detector of its kind to provide pitch angle resolved data in low Earth orbit, essential for the prediction of radiation dose received by astronauts both inside and outside the International Space Station. This new technology will lead to improvements in astronaut safety, advances in space weather prediction, and can characterize radiation energy input into the atmosphere for studies of climate change. Also, having applications in the radiation and medical isotope industries, SWEPT will maintain Canada's international reputation for excellence at the forefront of this niche area. In near-Earth space, high-energy radiation causes damage to satellites and various subsystems of the International Space Station. This can impact the operation of electronics and computers through single-event effects, or by surface and deep charging effects. Outer materials such as solar cells or optical components can become degraded. Higher energy radiation also penetrates deep into the spacecraft structures, creating secondary particles such as neutrons, which are a particularly hazardous form of radiation to human health. The main sources of primary radiation in low Earth orbit are galactic cosmic ray particles, solar energetic particles, and particles trapped in the radiation belts. All of these sources must be considered when planning space missions. Galactic cosmic ray particles are a form of radiation originating outside the solar system. In low Earth orbit, this radiation can interact directly with spacecrafts and humans and generate further space radiation through the production of neutrons in the upper atmosphere. Blasts of solar energetic particles arrive at Earth following solar flares. In the solar atmosphere, the temperature is so high that electrons and protons can escape the sun's gravity, continuously streaming out in all directions, forming a solar wind. Occasionally, this stream can be interrupted by more violent outbursts, solar flares. These eruptions generate solar energetic particles that can cause a surge of extremely intense space radiation. Fortunately, most radiation from the Sun is harmlessly deflected around the Earth by its magnetic field, forming the cavity known as the magnetosphere. Some radiation is able to penetrate the magnetosphere though, becoming trapped in the Earth's magnetic field, forming hazardous radiation belts. A larger outer belt contains mainly highly energetic electrons, while a smaller inner belt contains a combination of electrons and protons. Both are radiation hazards to the International Space Station. Particles trapped inside the radiation belts travel in spiral paths along the geomagnetic field lines. As the magnetic field strength increases closer to the Earth, the angle between the particle's motion and the magnetic field, the pitch angle, increases, until the particle reflects and reverses its direction, bouncing back and forth along the field line. The altitude of the mirroring is determined by the pitch angle at the equator. When the pitch angle is small enough, then the radiation can reach the astronauts on board the International Space Station. These particles scatter before they can bounce, raining down into the atmosphere, representing an important but poorly understood atmospheric energy source. In addition to their bouncing motion, trapped particles drift slowly around the Earth in a direction determined by their charge. Electrons eastward, ions westward. The combined effect of the particle motions causes a strong asymmetry in the particle fluxes. The steerable design of the SWEPT detector enables this asymmetry to be resolved. The Earth's magnetic field is tilted and offset with respect to the rotation of the Earth. This causes the field near the surface to be unusually weak in a region above the South Atlantic Ocean, known as the South Atlantic Anomaly. The radiation belts are closest to the Earth in this region. The orbital inclination of the International Space Station is such that it periodically passes through the South Atlantic Anomaly, where it receives the strongest radiation dose. The measurements provided by SWEPT will enable both the intensity and direction of the incident radiation to be measured. Understanding the radiation dose is important for future satellite missions as well as future space explorations, since missions to Mars will likely involve staging and construction in this orbit. SWEPT is based on a well-understood technology and builds on the instrument heritage from previous mission development. This makes it ideally suited as a low-risk technology demonstration on the International Space Station. SWEPT will consist of high and low energy detectors. These detectors are surrounded by a shielded housing with a single entrance aperture, enabling directional detection. Particle energy is determined by the penetration and energy deposition into a stack of silicone detectors. The critical SWEPT innovation is the ability to sweep the detector look direction, enabling full characterization of the space radiation. This is possible on the International Space Station, but would be impossible on a satellite. In addition to spaceflight qualification of niche Canadian radiation technology, data from SWEPT will have broad and far-reaching applications. SWEPT will address the need for improved radiation monitoring for astronaut safety at the International Space Station, will assess the radiation energy input to the atmosphere for climate studies, and will examine the space weather impacts of the radiation belt loss. Down here on Earth, applications include characterizing radiation beams for both dosimetry and testing in the Canadian radiation and related medical industries. Much further afield, SWEPT will provide Canada with the radiation technology essential for future space exploration missions to the Moon, Mars, and beyond.